Yes, pretty much. And then live stream this one. What's that? It's SCI33205 M605 76, sorry, 6.8.2021. And then yeah, nothing. It's soon to you. Right. And so one. All right. Yeah. Excuse. Okay. Using Thailand. Application. Starting.
โอเคพูดได้
นะครับก็กดอัดแล้วนะครับสามารถพิมพ์ชื่อมาได้เลยครับมีสุภวิทย์นะครับสุภวิทย์มาแล้วนะครับพัสสิทธิ์มาแล้วนะครับที่นั่นพิมพ์use this then use the technologyธนากรนะครับมาแล้วฟิล์มก่อน It's 605 14 to 16 to 16 and then save. Copy. Đen rồi. Oh my. Đây là phim. Nó phải. Nó phải rất là tốt. To select, to use the one. 278 this state ก็ไม่ไปอยู่ดี I don't know why อันนี้Yeah, we have to go to this. Volume, volume. So, let's say this one. This one. 18.16 ข้างแล้วก็4 2 3 Let's see what's going on. All right. So good. ถ้ามีอะไรสีแดงได้ยังมี So good afternoon, everybody. Welcome you to SCI33205 มีพีรทัศน์เข้ามาไม่มีใช่ไหมYeah. Welcome you to SCI33205 physics number 4. This is for section for the class M605, right? And yeah, so 3 people นะครับที่ซูมก็ที่ YouTube นะครับก็ไลฟ์ไปให้นะครับคุณเปิดหาเองครับหรือว่าจะให้ผมส่งให้เพราะว่าเดี๋ยวเปิดไลน์ก่อนไลน์สำหรับคนที่จะดูที่YouTube นะครับ ครับแล้วก็สัปดาห์หน้าครับวันพุธถ้าใครสนใจอยากเข้าเรียนวันพุธสัปดาห์หน้าเรายังย้ายมาพฤหัสอยู่ครับจะมี3 สัปดาห์what else yeah the ส่งลิงก์ที่ YouTube ให้นะครับถ้าใครอยากดูที่ YouTube นะครับสัปดาห์หน้าครับถ้าใครอยากเรียนร่วมกับม.6 สาธิตองคลักษณ์นะครับแต่ว่าเขาก็เหมือนคุณนะครับไม่มีการตอบอะไรเท่าไหร่ครับก็อยู่นิ่งๆของเขานะครับก็จะประมาณนั้นนะครับก็สามารถเข้าได้นะครับเวลาเดิมของคุณนั่นแหละครับแต่ว่าหลีกให้เขา3 สัปดาห์เนื่องจากว่ามหาวิทยาลัยขอผมไว้ตั้งนานแล้วผมก็เลี่ยงปฏิเสธครับปรากฏว่ามีปัญหานิดหน่อยครับก็เลยต้องเข้าไปสอนอีกให้เขานะครับเพราะว่าปีแล้วผมรับมาตลอดครับ Alright, now let's talk about our stories in okay, most of you let's remind again we สุภวิทย์พัสิทธิ์นะครับฤทธินันท์ณัฐวินธนกรกรนะปฏิหารวชิรวิทย์นะปณธรวาลินปีรทัศน์ปฏิหารภวัฒนนทกรภวิทย์นะครับokay now let's talk about I think I have recorded on it right here let's talk about our stories for M605 right here we arrived at almost at the end of this chapter this one okay let's remind ourselves let's remind ourselves we all right who else nothing more yeah the next topic we will talk about is the determination of induced currents and so on in yeah and after that after we consider several cases for the induced current determination, we will have 3 or 4 examples. Okay, a couple of examples and in the no กดผิดนะไปอยู่ใกล้กันด้วยin those examples we need to use this formula. Okay, this one the Faraday's induction formula. All right, yeah, with this one, right, yeah, let's remind ourselves epsilon is equal to minus n and delta phi b divided by delta t, right? And then phi b is going to be something here, right? bt, at, and cosine phi t. So it can happen that all those 3 variables, which are magnetic flux, magnetic field, the area of the conductor, or the angle of the conductor, can change with time. All right, in that could also be possible in for us. I'm not sure whether you can see whole thing here. ยังไปอยู่ครับหน้าจอไปอยู่เลยผมแชร์แล้วนะไม่ได้แชร์เหรอไม่แชร์หน้าจอไมค์ก่อนพูดไปเซิร์ฟเวอร์เลย All right Okay, we arrive at this page สองคนนะครับวันพุธหน้าถ้าใครอยากฟังเรื่องแต่คุณติดเรียนเนาะคุณติดเรียน605ครับก็เว้นไปเหมือนเดิมครับ alright yeah we arrive here at the formula by Faraday okay the formula by Faraday will give you the amount of will tell you about the induced EMF. Okay, it has negative value because it acts against the straightforward direction, the forward direction of the magnetic field. Okay, because this one, the induced EMF happens due to the change of the flux. Okay, which is this factor, and its strength depends also on n. Okay, and we will see that those three variables, the magnetic flux, the area, the angle between normal of the conductor to the magnetic field. This is the angle. Okay, whether it changes with time or not. Okay, if it changes with time, usually it's gonna happen in generator. Okay, electric generator, which is the next topic after this one, and it can happen that the area it can change. Okay, but this is the very special scenario, and the case when the magnetic flux changes. This is what we อาจารย์รับผมเข้าด้วยครับว่าริวไม่มีว่าริวพิมพ์มา1233ว่าริวเข้าWhat happened?นะครับอยู่ดีก็หลุดนะครับไม่รู้อินเทอร์เน็ตผมไม่ดีหรือว่าอย่างไรไม่ตรง 5G นะเราเสียบที่นี้นะครับใช้อันนี้ดีกว่า 5G ไม่มั่นใจอันนี้ครับของมหาวิทยาลัยผมก็เสียวเหมือนกันครับมหาวิทยาลัยวิ่ง1 กิกครับแต่ว่าใช้จริงไม่ได้เรื่องครับก็ไม่รู้เกิดอะไรขึ้น change to 3 technology 604ยังไม่เจ๊งเลยนะครับนี้เห็นหมดทุกคนละนะครับจะประมาณนี้มีคนอยู่จะประมาณนี้ครับแล้วก็แชร์หน้าจอไม่ทราบว่า กำลังจะเริ่มเลยครับดันมีปัญหาอินเทอร์เน็ตนะครับ604เขายังไม่มีเลยครับwhat else all right we go ahead with our story yeah there are three variables b a and cosine phi t all right in it kind of that all these three variables, three quantities, can change with time whether the magnetic field, the area, or the angle between the normal vector of that conductor and the magnetic field, right? And อันนี้แค่ทบทวนครับ and Len says that the induced EMF acts as to oppose the change in flux that produces it. Okay, if you don't understand the word, there's no problem. Let's consider this scenario. You're gonna understand what Lens said. Okay, ถ้าไม่เข้าใจก็ดูตรงนี้เอาละครับเราจะรู้ว่าสิ่งที่เลนพูดหมายความว่าไง Okay, now let's start the Lens statement. Well, here you have the permanent magnets, permanent magnets, right? แม่เหล็กถาวรครับใช่ไหม and in any magnets, whether it's permanent magnet or any other types of magnet, there should be two poles, right? The south pole and the north pole. Now let's start with the typical way. Okay, we lay down the north pole toward the plane, okay, the planar surface of the conductor. This is the loop of the conductor. Okay, in let's see what's going on. At the first state, okay, we leave the permanent magnet like this, and of course, in the typical way at the beginning of this chapter, at the north pole, we are going to have the magnetic field line, right? Going away out of the north pole, right? In this magnetic field line is gonna turn and get into the south pole. Okay, and that's in the beginning of this chapter. Okay, and that's the first thing. Okay, and after that, in the second situation, we will move it toward the conductor. All right, in yeah, that's what a person, that's how a person move the permanent magnets. But let's take a look at the feeling of the conductor. Okay,เรามาดูที่ความรู้สึกของขดลวดบ้างนะว่าเขาเป็นไง Let's take a look at the feeling of the conductor here. At the beginning, the permanent magnet is quite far from him, right? And the magnetic field line is just directed towards him, and yeah, he feel that there is magnetic field with a certain amount, okay, pointing to me, okay, directed to me. And after that, someone moves these permanent magnets, and if we are inductor, right, we will find that the magnetic field is stronger when someone moves this permanent magnet, right? And he find that I'm serious, I'm in the pressure because someone leave more magnetic field to me. Okay, and let's take a look at the vector statement. Here is the first situation. Okay, the conductor receive the magnetic flux with this length, okay, which represent the magnitude of the magnetic flux. And in the second situation, when someone moves this permanent magnet towards him, toward the conductor, he would get stronger magnetic flux, which is this one, okay, which is phi B2, okay, phi B1 represent the magnetic flux for the first scenario, the time T1, and the second scenario, phi B2, okay, represent the flux at time T2. And what happened is in physics, it means that this guy, the conductor, would feel that there is increasing flux to me. Okay, you just make the subtraction between the second vector to the first vector, right? Which is the typical way in physics, right? Because we have to, when we want to say or observe the difference in physics, okay, the typical way is that final state minus initial, right? The initial state, right? And that's also the same thing. Phi b is phi b2, delta phi b is phi b2 minus phi b1. So that's why we get the additional length of the increase in the incoming magnetic flux like this, okay, delta phi b. But the inductor is like a lazy person, okay? He is I don't know, inertia, okay? He is lazy. He doesn't like someone who changes the environment to him, okay? He doesn't like the change with him. So no, someone leave more magnetic flux toward me. He needs to act against this increasing amount of the magnetic flux by generating the magnetic flux in the opposite direction, but with the same amount of this one. Okay, it's not exactly the same. You have to convert. You have to divide phi is equal BA, right? You have to divide this one by A. You will get B. Okay, B. Okay, B induced absolute B induced is equal to phi delta phi b by A. Okay, the area, the cross-sectional area of this conductor. Okay, all right, this is the relation. We have to generate the magnetic flux in the opposite way to the flux change. Okay, when someone moves the permanent magnet towards the conductor. Okay, and this is the Lenz statement. Okay, he said that the conductor should produce the magnetic flux, okay, to compensate or to get rid of, to remove the increasing amount of magnetic field. Okay, if the permanent magnets stay like this all the time, nothing is going to happen at all. All right, but if someone move this permanent magnet toward the conductor will be unhappy and he will act against that increasing amount of the magnetic flux, okay, by generating this B field. Okay, and in order to have B field, okay, the conductor doesn't have any energy at all. Okay, he has to generate the energy itself, okay, in order to get this one. Okay, and then in order to have the magnetic flux in this direction, okay, to act against the increasing amount of flux change, he has to generate the currents, and the direction of the generated current should follow the right hand. Okay, you leave your thumb direction to this one. Okay, your thumb direction นิ้วอะไรนิ้วโป้งนะครับโอเคไหมมือขวาคุณนะ your right hand, okay, the thumb on your right hand, lay your thumb on the right hand according to this vector. You will get the direction from your 4 remaining fingers. Okay, you have 4 remaining fingers, right, apart from the thumb one, and then you have other remaining 4 fingers, and the 4 remaining fingers will tell you the direction of the current that should be. Okay, because usually if we have the current, we will be able to find the magnetic field too, okay, by using the right hand. It's in the same in a similar way. If we want to find the currents direction from the magnetic field, we should apply also the right hand and your 4 remaining fingers will represent your 4 remaining finger will represent the current. Okay, when you lay your thumb, okay, as direction of the induced B magnetic flux. Okay, that's the situation when we move the north pole to the conductor. Now let's consider the situation when we move the south pole of the permanent magnet toward the conductor like this. Okay, and you know that in the permanent magnet or any kind of magnet, the north pole is the place where the magnetic field line start, okay, to go out, right? But on the other hand, in the south pole of any magnets, whether it's permanent magnet or electromagnet, okay, the south pole is the place where the magnetic field lines try to get into. Okay, the magnetic field lines try to get into the south pole, and yeah, it's not the main thing for us. The main person is the conductor here. Okay, the conductor will feel that there is magnetic field line pointing toward the south pole. Okay, he would feel that I have magnetic flux pointing upward. Okay, that's the feeling from the conductor. But if you move it toward the conductor will feel that I get stronger magnetic field lines, but that points upwards. Okay, it's opposite to this one. He gets the stronger magnetic flux, but with direction with a downward direction. But here the magnetic field line is pointing upwards. All right. And what else? Yeah, in the first situation, you have 5B1. That's the magnetic flux pointing upwards. And when someone moves the permanent magnet to be closer to the conductor, the conductor feel that there is stronger magnetic flux, which is 5B2. And in physics, if we want to see any difference, it's the final state minus the initial one, right? So 5B2 minus 5B1 will be delta 5B, okay? And 5B is the change of the flux, which is what the conductor doesn't like, okay? The conductor doesn't like the change of the flux at all, and he tried to get rid of these amounts by generating again the magnetic field, which is pointing in the opposite direction to the flux change, okay, in the opposite way. And its relation can be found easily from this one by using this expression, okay, this relation. And yeah, the current cannot have this induced magnetic flux, except that he generate the currents, okay, around himself, and the direction of the generated current should follow the right hand. In order to get the magnetic field in this direction, you lay down your thumb, okay, lay down in the same way as the induced magnetic field, and you would get induced currents, okay, on the conductor loop. All right, and that's the whole story, all the mechanism that happened in the movement of permanent magnet toward the conductor. Now let's consider the second group when we move the permanent magnet out of or away from the conductor, okay, whether it's north pole on the side, okay, and the south pole close to the conductor, okay, the south pole on the right side, okay, and yeah, we will see what happened. ตอนนี้ผมขออนุญาตเข้าห้องน้ำแป๊บนึงครับเดี๋ยวมาหน้านี้ให้จบนะครับ Okay, now let's consider the second type of movement for the permanent magnets. We move the permanent magnets away from to be away from the conductor. Okay, the circular or any shape of loop. What the conductor field is that there is magnetic field lines pointing throughout his surface, right? In the vector that he can feel is phi b1, right? Phi b1 like this. But in the second scenario, someone moves this permanent magnet, this object, away from him, and it means he will get lighter magnetic field. Okay, the strength of the magnetic field is going to be lower. Okay, he get less amount of magnetic field, so the vector representation for that amount should be shorter, like this. Okay, phi b2 is shorter than phi b1, and according to the typical way of in physics, okay, a difference could be observed again, okay, by final state, right, minus initial state. Initial state. Yeah, we make the subtraction between phi b2 and phi b1. We get the negative value, right? Because this final state is shorter. Okay, final state is shorter than the initial state, so we get something negative. So the negative value means the opposite direction of the vector. Okay, all two vectors are pointing in are directed to the low part, right? So here we have upward vector. Okay, the vector pointing upward, and the magnetic the conductor doesn't like the change of the flux at all, which is pointing upward. He tries to compensate or to make the balance, okay, or to get rid of the increasing amount of flux by generating the magnetic flux pointing downwards. And if you lay down your forefinger, your thumb direction, okay, you lay your thumb direction down as direction of be induced, you get the current direction from your 4 remaining fingers, okay, with this one. Okay, ใช้กดมือขวานะครับเรามือโป้งชี้ลงตาม b induced นะครับ vector b induced ครับคุณ4 นิ้วของคุณก็จะแสดงทิศของกระแสที่ได้ผลลัพธ์ครับไม่ว่ากรณีใดก็ช่างโอเคไหมครับจะเหนือเข้าเหนือออกหรือว่าใต้เข้าใต้ออกนะครับขั้วใต้ครับโอเคnow let's consider the second scenario for the second type. Okay, we move the permanent magnets away from the conductor. So here is the south pole, right? The magnetic field realize that there is magnetic field lines passing through him and pointing upwards. Okay, pointing up. And what else? Someone moves these permanent magnets to be away from him. Okay, at the beginning he get quite strong vector, quite strong magnetic field line pointing upward. Okay, phi b1 is quite large, and when someone move it out of him, he will get the magnetic field shorter, okay, lighter, which means shorter vectors. And again, we apply the difference in physics, final state minus initial, phi b2 minus phi b1. Okay, the final state is shorter, right? So it's going to be negative value, and the negative value means the opposite direction of that vector. Okay, of those two vectors. This is the flux change, okay, observed by the conductor. All right, the conductor is a lazy person. Okay, he doesn't like someone to disturb him. Okay, he tried to get rid of this chain, okay, the flux chain, by generating the magnetic flux. Okay, and in order to get that magnetic flux, he has to let the current flow in any certain direction. And in order to find any certain direction of the current, we should apply the right chain again. Okay, you lay down your thumb, okay, pointing upwards, okay, as same as be induced, and you will get the direction for the current from your 4 remaining fingers like this. Okay นะครับลองจินตนาการวางตามนะครับเพราะว่าสวิตช์เป็นกล้องมันก็จะวางครับพี่ผู้ชวงวัดมาที่ YouTube ด้วยนะครับเซฟไว้ให้ครับ and yeah now you understand, right, how the current generation, how the current can be generated in the conductor. There is no battery, there is no power source at all in all these 4 cases. Okay, the current just was just generated himself, okay, in the conductor in order to get the be induced, okay, to act against the flux chain, okay, in all those 4 scenarios. If you have any questions about these 4 situations, just let me know. If not, we go ahead with some figures from other books. Okay, this is taken from another book. Okay, all these 4 figures are taken from one book, and this from another book. Let's say if we don't have the current at all, okay, nothing. If we don't let the current flow in this one, there will be no current. And if there will be no current in this conductor, this is the conductor loop. Okay, it doesn't matter whether we have the conductor loop in rectangular shape like this, or in circular shape, or in any shape. Okay, the important thing is that it should be the closed loop from the conductor. Okay, the closed loop of the conductor. Okay, but if someone disturbs this situation by letting the current flowing up, okay, by using any battery or any water source, and in that case there is current flowing upward like this, and from the Ampere's law, okay, we could apply the right-hand rule, and the amount of the magnetic field could be found from the Biot-Savart formula, like B equal mu0 I divided by 2 pi d or 2 pi r, right? If you are far away, you get weaker amount of magnetic field. Yeah, this conductor just stay quite close to the straight, long straight copper wire here, and that has current flowing too, right? And there would be also magnetic field lines that pointing into pointing throughout the surface or the area of this conductor loop, the rectangular conductor loop. And yeah, if you are the square, I don't know, the rectangular conductor loop, you will find that at first there is no magnetic field pointing through me at all. But when someone let the current flow, there are some magnetic field lines pointing into me, okay, into my cross-sectional area. This guy will not be happy at all, okay, because someone disturbed him. Okay, conductor like the peaceful situation. Okay, he doesn't want anybody to disturb him, okay, or to annoy him. And then yeah, he would try to generate the current in order to get rid of the increasing amounts, okay, the magnetic field is pointing to me, to him in this scenario. He will try to generate the magnetic field in the opposite way and with the same amounts. Okay, he will not produce the magnetic field greater than that amount, okay, because it's beyond his requirement. Okay, he just want to remove all anything that changes his cross-sectional area. And in order to get the induced magnetic field, he has to let the current happen and flow in this direction. Okay, it can't flow in this direction from upper to lower because the magnetic field line is going will point into this plane, right? And it's gonna accumulate this previous magnetic field, okay, from the disturbance. He has to let the current flow in this direction so that there will be induced magnetic field pointing in the opposite way to these magnetic field lines. All right, and yeah, this one should be equal to this one, so that there will be complete cancellation. Okay, there will be full removal of the exceeds magnetic field. Okay, and yeah, we apply the right hand, we can get the current direction like this. All right, เดี๋ยวเราอะไรนะ15 40 ใช่ไหมครับผมต้องปล่อยคุณอีกประมาณ34 นาทีครับ as the here is taken from another book, but it's quite close to all those 4 situations, right? That is south pole of the permanent magnet, that is north pole of the permanent magnet. South pole is the place where the magnetic field lines will try to get into, right? And north pole is the place where the magnetic field line start to get out, right? And yeah, it's not the important thing. The conductor is the main person that we have to take care. He will realize that, he will understand that there is magnetic field lines pointing through his surface like this, okay, and that's the first situation. But if someone move this magnetic field line with the velocity vector v towards the surface of this conductor, this conductor will find that I get stronger magnetic field line, someone disturb me, okay, and he will find that he doesn't like the stronger magnetic field line, okay, because someone moved the permanent magnet to be close to him, and after that he will try to get rid of, to make the cancellation of the excess magnetic flux, okay, by generating the magnetic field in the opposite direction to this one. Okay, if you move this one to the conductor, then there will be more magnetic flux from left to right, and he has to reduce this amount, okay, to be in the same level as before. So he will try to generate the magnetic field in the opposite direction from right to left, okay, and he cannot produce it himself, okay, he has to generate the currents around him, okay, by using the right hand rule, the thumb direction laying down here horizontally, and your all 4 remaining finger will represent the current that should flow, okay, and that's the idea. All right, yeah, that's what happened. Okay, I forgot to mention, N can be considered as the north pole of this magnetic field generation, okay, induction, and on the right side we could imagine that this is the south pole, because in the south pole we have the south pole is the place where we get the magnetic field line getting into, right? And north pole is the place where we have magnetic field line getting out of, or start to get out, right? What happened? Internet, it's over or what? Not fine. Oh, internet maybe. Okay. ครับอีกเครื่องนึงอินเทอร์เน็ตมหาวิทยาลัยใช้ได้ไม่ดีไม่งามครับใช้เวลาจำกัดดีไม่ซูมไม่เตะออกครับไม่คลิกก็ผมเอาครับอินเทอร์เน็ตขาด okay, yeah, that's the scenario, and let's consider another case when we have electromagnet. Okay, electromagnet is a little bit different from permanent magnet. Okay, permanent magnet ก็คือแม่เหล็กถาวรครับ electromagnet ก็คือแม่เหล็กที่เกิดจากไฟฟ้าใช่ไหมครับมันเป็น it's not permanent magnet, it's temporary magnets. Okay, and its source is electricity, right? You have battery, and you put the energy from the battery, you let the current flow from the plus side, plus polarity of the battery to the conductor, and you let the current flow from the another end of the conductor to the left, to the negative side of the battery. Okay, and that's called electromagnet. Okay, unlike permanent magnet is not complicated. Okay, it's a special behavior of metal. Okay, that has an equal amount of electrons in some orbits. All right, and yeah, the solenoid has been wired around a core. Okay, this core is of the cylindrical shape. Okay, the core is cylindrical, and yeah, when you open the switch, okay, there will be no current movement, right? There is no current movement because this switch is open, and when there is no current, there will be no magnetic field also in the core. Okay, and there will be no magnetic field lines passing through the surface, the inner surface of that conductor, of this conductor, right? Yeah, and let's consider the second situation when you close the switch. Okay, the switch is closed, and the circuit is fully connected, and the current will start to flow from the positive side polarity of the battery and turning around according to the solenoid shape. Okay, and yeah, like this, and the current will flow like this. Okay, to the minus polarity, the negative polarity of the battery. All right, but that's the whole story about current movement inside the solenoid. It's not the main thing. The main thing is there will be magnetic flux. Okay, and if you apply your right hand, okay, according to the direction of current movement, you will get you lay your forefinger as same as the direction of the current movement in the solenoid. You will get the thumb direction as the magnetic field direction. Okay, which is the magnetic field pointing into the core. Okay, like this. มันไม่เป็นอย่างนี้เสมอไปนะขึ้นกับทิศทางการพันขดลวดคุณนะใช่ไหมครับแต่เขาพันอย่างเงี้ยก็คือเส้นลวดมันเข้าไม่ใช่เส้นสนามแม่เหล็กมันเข้าแกนครับ so the conductor will realize that you feel that he will feel there is magnetic field pointing to him, right? In does he like? He will not like at all. Okay, because someone disturbed him when we turn on the switch. He has to wait in this scenario. We will not talk about the third figure yet. Okay, let's completely consider the second figure. When there is current move from the right to the left like this, he doesn't like this situation because someone tried to disturb him. He will try to generate magnetic field in the opposite way. Okay, in the opposite way, and yeah. In order to get the magnetic field in the opposite way, we will apply the right hand. Okay, lay down our thumb direction of your right hand in this direction. Okay, towards the opposite direction to the magnetic field. Your 4 remaining fingers will represent the current flowing inside the conductor. Okay, and that's the situation when we close switch. Okay, when you let the time goes by, the conductor will be able to accept the dense, okay, the dense magnetic field. Okay, and if you now we move to the figure number 3. If we open the switch, okay, before that he get an amount of magnetic field, right? And when we open the switch, there will be no current move at all in this one, and there will be no magnetic field lines. And this guy again, he doesn't like that situation when someone disturb him. Okay, before that he get a large amount of magnetic field lines, and after that there is no magnetic field lines, he has to generate the magnetic field line in the same way as this one, okay, because he wants to keep the situation same as before, okay. So the direction of the magnetic field that should be generated is this one, okay, from right to left. And we lay down our time direction, we will get the direction of the current, induced current from our 4 remaining figures, which is this one, okay, the currents. All right, now we complete all the explanation about the determination of direction of the induced EMF. Now we arrive at the example. We will apply the Faraday's law of induction, which is epsilon E equal minus n delta phi b by delta t, right? Let's consider figure 78. In the region between the poles of the electromagnets, there is uniform magnetic field, and yeah, this device, okay, it's a special device. I would not see that I won't expect that we could find it in daily life. Yeah, it's a special device. It's this device that can generate magnetic field from north pole to the south pole, okay, from the lower pole to the upper pole, okay. More importantly, this device can change the amount of magnetic field, okay, the B vector. And we have another device, another object, which is let's say it's conductor, okay, conductor, and laying down, not laying down, it's above this magnetic pole, and one end of the conductor is connected to the ammeter or voltmeter. I think voltmeter is better because we are talking about the induced EMF, right? EMF is equivalent to voltage. So another end of the conductor is also connected to another side of the voltmeter, and yeah, it doesn't matter if we have the circular shape or square shape or any type of shape of the conductor. Okay, the important thing is that there is cross-sectional area, which is 0.012. All right, yeah. They ask for the magnitude, okay, the magnitude of the induced EMF and the induced current, okay, two quantities. Now let's solve this one. The magnitude, right? Now, before we go to the magnitude, let's formulate the basic formula by Faraday's law. It's Faraday's law, okay? It's not Friday law. It's not the law of Friday. All right, it's Faraday's law. So this one, Faraday's law, right? It's epsilon equal or minus n and delta phi b divided by delta t, right? That's Faraday's induction law. And when we have to use the basic formula at the beginning of this chapter, phi b is b. Oh, sorry. Phi bt is equal to bt, okay, magnetic field depending on time, at cross-sectional area depending on time, and cosine of phi t, okay, which is the angle between the norm of the conductor to the magnetic field. That depends on time, okay, which is written with the parenthesis and the variable t here, okay. this one, okay, we cannot substitute this one directly to this one because in several problems some variable may change, but at the same time another variable may not change. Okay, we cannot simply substitute this one to the main formula directly. So what they say is that bt change, okay, here bt per delta t, it means the not bt. The magnetic field delta b change with time, okay, it's 0.02 Tesla per second. So delta b is equal to 0.2 Tesla per second, like this, and a at, okay, at is, oh no, I'm stupid. It's not delta b with 0.2 Tesla per second. Okay, we will simply see that. Okay, bt is not constant, so I don't know what is the bt, but they say delta b by delta t is, what is that? Is 0.02 Tesla per second, right? In bt and then at, which is the cross-sectional area with respect to time. Does the area change in this scenario? In this figure, no, it doesn't change, right? In both situations, the area of the cross-sectional area, the area of the conductor loop doesn't change at all. So at is going to be a. And what type of this one? They say, they didn't say anything. They just say 12 120 square centimeter, right? And let's talk about phi t. Phi t, that's the angle of the conductor change with time. Is there anyone who change the location of the conductor? No, right? The conductor just stay like that. And phi t is going to be 5. And in this case, the normal vector is going to be like this. Okay, the vector that is perpendicular to, this is normal vector, this is normal vector, normal in any direction. And you will find that the angle between the normal vector and the B field, the magnetic field, is 0, right? Because both are pointing, both are directed in the same way. Angle between vector N and vector B is 0, so it means phi is 0 degree 2. So now we will substitute it into this one. So 5 is 0 degree, right? And yeah, and what else? Nothing more, right? Let's start with the Faraday's formula. Epsilon is, oh no. Because they ask us about the magnitude, right? The magnitude quantity. So we cannot simply use epsilon directly. We have to take the absolute value to both sides of this equation. This one, the Faraday's induction law, and we will talk about it. The absolute value. Well, absolute value of epsilon is going to be the absolute value of minus I on the right side, and delta phi b by delta t, right there. And in mathematics, the absolute value will can be spread to several objects, right? So it's going to be absolute value of minus n and the absolute value of delta phi b and delta t, right? ผมว่าเขียนอะไรไม่ค่อยมีศิลปะอะไรเลยนะครับ delta delta t, right? And yeah, oh no, absolute value too, right? On the right side. Yeah, That's it. But later we use n, right? N, what is n in this scenario? Number of turns. They didn't say it all, right? But please take a look. Please have a look at the figure. What do you think then about the number of turns in this conductor? How many turns should we have? From what they draw, there should be only one turn, right? So n in this case is one turn. Okay, even they didn't say it in the problem, you should be able to realize yourself. Okay, and what else? Yeah, minus n is the absolute value of -1, right? My God, it has nothing to do at all. And in this case, let's summarize this one. With all these three things, we would find that delta phi b will be phi 2 minus phi 1, right? Phi 1 is no. We cannot induce that. Delta phi b will be delta b, right? And then a, right? A and cosine of what? Cosine 90, cosine 0, right? Cosine 0 times delta phi b is delta phi b ba, right? So there will be delta b here. Okay, delta phi b is going to be something like that. So we have here a cosine 5, but in this case 5 is 0, right? Yeah, 5 0, so it's going to be a and delta b, right? Yeah, we move. Oh. Yeah. So a delta b, right? Delta phi b is a delta b. A delta. This is a. This is a and delta b divided by delta t right here. And yeah, we go ahead. It's nothing at all. It's only number 1, right? This one. A is the area, right? Which is 120 square centimeter, or you divide by 10,000. So you get 0.012, right? 0.012 meter square, right? It's not centimeter. We want to represent it in SI scale so that we can get this unit for the EMF easily, which is what, right? In yeah, delta B. Oh no, it's only A and delta B by delta T, right? In the delta T that they have provided is 0.02 Tesla per second. Tesla per second. Oh. 0.02 Tesla per second, like this. Yeah, and if you leave it into the calculator, actually you don't need to have, you don't have to do that. It's going to be 0.00024, right? And the unit for the EMF is volts, right? And if you don't like this one because there are too many zeros, okay, it's not clean, you can leave it as 0.24 and millivolts. Okay, and that's it for the first quantity. Let's check with this. Yeah, 0.24 millivolt. Now let's consider the second question. What is the induced current? Okay, when we want to find current, we have to look for the resistance, which is what they have provided here. 5 ohm. Okay, all right. We open a new page and we're gonna apply the Ohm's law, right? VIR. Okay, this is Ohm's law, right? Yeah. Ohm's law say the VIR, right? So we want to find I, you just hide the variable I, so it's away from this triangle. You will get I equal V, okay? But V in this scenario is the epsilon, so it's epsilon by R, right? Epsilon is 0.00024 volts, right? And divided by R. R is the resistance, which is 5 ohm. Okay, 5 ohm. Oh, 5 ohm. Yeah, and then you will get 0.00048 ampere. All right. If you don't like it, you may want to write down it as microamp. It should be 48 microampere, and that's it for the second quantity. The second quantity, which is the current. All right. Yeah. Let's take a look. Let's have a look at it. Okay, 48 microampere. Okay, exactly the same thing. Now we move to the second example. Now let's have a look at the second example. All right. I don't know how many turns do we have here. You can't just count it by eyes. Okay, you may get a failure. Okay, you may get an error from that. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, you cannot conclude that this conductor has 9 turns. Okay, you can use number 9 if they don't say the information of the number of turns at all in the question. Okay, but let's have a look. A coil with 25 turns of Y. Okay, but it's not 25 here in this figure. It's there are 9 turns of conductors in this one. Okay, you cannot use n equal to 9 to this figure because they have provided the exact value here. Okay, and we have here n equal 25 turns, right? Turns is wrapped on a frame with square cross section 1.8 centimeter on a side. Okay, this is very, very important because many of you have done the homework wrong. Okay, you get failed in the homework because you don't understand the meaning of square cross section on a side. Okay, ตรงนี้นะครับที่คุณผิดมากนะครับในการบ้านนะครับโปรดอย่าผิดนะครับเวลาทำข้อสอบนะครับการหาพื้นที่ของสี่เหลี่ยมจัตุรัสนะครับต้องเอาด้านมาเป็นไงด้านหนึ่งมันมี4ด้านใช่ไหมค่า4ด้านมันจะเท่ากันก็เอาด้านมาทำอะไรครับกว้างคูณยาวด้านมันคูณกันจะเป็นยกกำลัง2ใช่ไหมครับแต่สิ่งที่คุณทำในการบ้านกันมาคือคุณเหมือนว่าจะยกกำลัง2แต่คุณไม่ยกนะครับแล้วคุณเขียนว่าหน่วยเป็นตารางเมตรบ้างตารางเซนติเมตรบ้างเหมือนว่าคุณยกกำลังมาแล้วแต่ว่ามันไม่ได้ยกนะครับคุณเอาเลขที่ on a site เนี่ยค่าด้านเนี่ยไปใส่ในพื้นที่เลยนะครับซึ่งผิดนะครับโอเคไหมผมก็ไม่อยากตัดคะแนนนะผมตรวจไปผมก็เสียดายไปนะครับแต่ก็จำเป็นต้องตัดคะแนนนะครับในเมื่อมันผิดนะครับโอเคไหมก็ผิดตรงนี้ได้ครับโอเคไหมครับอย่าไปผิดตรงข้อสอบแล้วกันนะครับ เพราะว่ามันก็สำคัญนะครับ Okay, they say square cross section 1.8 on side. It means one side of this one. Okay, if you take a look in 2D system, the length of this one is 1.8 centimeter only. Okay, 1.8 centimeter, and that's it, right? Yeah, the area is the product between 1.8 centimeter to 1.8 centimeter. So the area here is going to be area of square. Equal 1.8 centimeter square, right? Is going to be ไม่ได้ครับ18 324หรือเปล่าyeah 3.24 square centimeter. All right, right there. Oh, sorry for that. True. Okay, don't leave the number 1.8 to the area. Okay, the area should have the power of 2 to the side. This and this is the area. Okay, and they say there is magnetic field change from 0 to 5. From 0 to 5 Tesla in a 0.8 second. What is the induced EMF when the field is changing? Magnitude and direction of the induced current when the field is changing. Okay, it's no problem. Okay, for the first quantity, the induced magnetic field, induced EMF, induced EMF can be found. So they didn't ask us about the magnitude, so we don't have to take the absolute value operator on both sides of that formula. So we're going to use epsilon equal minus n delta phi b. Okay, the basic formula of the Faraday induction law. Delta t, and we consider first phi b, which depends on time, right? Equal bt, at, and cosine phi t, right? Yeah. Now let's have a look at bt. What is bt? bt, b as a function of time. It changes from 0 to 0.5 in 0.8 seconds. So we cannot say there any value of bt, but we have some information that delta b by delta t is delta b by delta t is there over there, right? Which is b2 minus b1, right? And divided by t2 minus t1. Okay, we know that b2 is 0.5, b1 is 0, so we have 0.5 minus 0 divided by the time of observation is 0.8. Okay, and then yeah, you get the value for delta delta b by delta t 0.5 by 0.8. 0.5 by 0.8. Oh, 0.5 by 0.8. Yeah, it's 0.625. 625 Tesla per second, right? That's delta b by delta t. So let's have a look at this one. What about AT? dash the cross sectional area of จบข้อนี้ก็จะหมดแล้วนะครับdash the cross sectional area change with time no right the conductor just say like this there is no change with the shape of that conductor at all so at is going to be a okay which is a constant doesn't depend on time and it's equal to what we have calculated which is here 324 square centimeter or 324 times 10 raised to negative 4 square meter okay in SI unit and let's take a look at the last value the third value phi t is there any change in phi t is there any change of phi t in this figure the angle between the normal vector of this conductor to the magnetic field lines so it's not the case right so if you take a look at that this is the plane of the conductor right in here is the normal vector right normal vector and here is the b vector b vector b vector right b vector this is b vector so you can see that n is parallel to b so the angle between vector n and vector b is going to be 0 degree right so when we have once we have 0 degree phi t will be phi t will remain constant as phi and it's going to be 0 right yeah now let's make conclusion to phi bt okay phi bt is phi bt right phi b at time t1 t2 right it's going to be b I don't know bt as a function of t bt right and a right because it doesn't depend on time right a doesn't depend on time and cosine of what cosine of 0 degree right so it's going to be simply bt it will be a and bt right like this and yeah we will substitute phi bt a bt here into this expression epsilon is minus n in but this delta b by delta t right so in this case we would have a right a and delta b right by delta t right and you just move a okay to this one and minus n and a in times delta b by delta t like that okay yeah that's what's going on and now it's time to make the substitution minus n okay they say 25 turns so we have to lay down 25 turns in a cross sectional area is this one right 3.24 times 10 raised to 24 square meter okay everything in SI scale in delta b by delta t delta b by delta t is what we have already calculated here 0.625 0.625 Tesla per second all right and we put it into the calculator and we would find it what is that 25 turn minus 25 times minus 25 times 3.24 times what's up oh no No. Oh my God. 1 E. Oh no. Oh, this 1 10, right? This is too negative. 4, right? BA and what? NA delta B delta C, right? OO minus 25 A and delta B by delta C, right? Times 0.625, right? Times 0.625. Done. Generate. Okay, 0 point minus 0.0500625 minus 0.0050625. The unit for this is volts, right? And yeah, it's, if you don't like it, you can say it's minus 5.0625 millivolts. Okay, and that's it for the first quantity. Let's consider the second one, the magnitude and the direction of the induced currents. Okay, if you take a look at this one, okay, when there is magnetic flux flowing like this, okay, and the connector doesn't like, so there should be induced magnetic field in this direction, right? Okay, it flow down throughout this one, and that's delta phi b, right? Delta phi b. Okay, and in order to get this magnetic flux, okay, in the opposite direction, we have to generate the current, okay, to satisfy this vector. So we apply the right-hand rule, okay, laid out our thumb to this direction, and we'll find that our 4 remaining finger will give us the current in this okay, this one, okay, in this direction. The current should flow in this direction. Okay, because this direction satisfy the downwards magnetic flux chain. Okay, all right, and that's the answer for the direction. Let's consider the last question, which is the magnitude, right? Magnitude of induced currents. Okay, magnitude, when we talk about magnitude, it means it should be always positive, right? Okay, magnitude of I. So the magnitude of I is going to be this one, and it's absolute value VIR, right? We apply again the Ohm's law, V I and R, but I can be known in this topic that I is equal to the epsilon, right? Epsilon, and divided by R, right? Okay. And epsilon is this value, okay, is minus 5.0625 divided by R. Okay, the resistance in this scenario is 0.35. 0.35. All right, this is ohm, this is millivolts. Okay, and you put it into a calculator, you get the outcome, which is 14.46. okay, it's equal 14 4643 okay 4643 and the unit is milliampere. That's milliampere. Unit is milliampere. Okay, and that's for this problem. Okay, quite large and a little bit complicated. Okay, but it's not beyond our ability. โอเควันนี้นะครับสรุปเป็นภาษาไทยให้ฟังนะหมดเวลาไปเลยไป11 นาทีแล้วนะครับก็เราเรียนเรื่องทิศทางขนาดทิศทางของกระแสที่เหนี่ยวนำนะครับเวลาเอาสนามแม่เหล็กตัดขุดลวดนะครับทั้ง4กรณีนะครับตรงนี้นะครับก็ใช้กฎของเลนส์ไปนะครับโอเคไหมพฤติกรรมของลวดก็คือเขาเป็นคนเฉื่อยชานะครับไม่ชอบอะไรมาเปลี่ยนแปลงเขานะครับพอมาเปลี่ยนแปลงปุ๊บเขาจะทำตัวต่อต้านอยู่แวบหนึ่งครับแล้วก็สร้างกระแสขึ้นมาครับทิศทางอะไรก็สร้างสนามแม่เหล็กทวนต่อต้านนะครับตรงข้ามแล้วก็ทิศของกระแสก็ใช้กดมือขวานะครับนิ้วโป้งชี้ไปตามสนามแม่เหล็กนิ้ว4 นิ้วที่เหลือเป็นทิศของกระแสนะครับอันนี้ก็คล้ายๆกันนะครับไปเปลี่ยนแปลงสนามแม่เหล็กก็ทำให้เกิดกระแสนะครับอันนี้ก็เหมือนกับรูป4อันนั้นนะครับรูปนี้นะครับส่วนอันนี้ไม่ได้เคลื่อนทางกลโอเคครับไม่ได้เลื่อนไม่ได้เลื่อนแม่เหล็กเข้าออกกับตัวขดลวดนะครับเพียงแต่ว่าใช้อะไรใช้สวิตช์ทางไฟฟ้าก่อให้เกิดการเปลี่ยนแปลงสนามแม่เหล็กแทนนะจริงๆมันก็คือสิ่งสำคัญคือมีการเปลี่ยนฟลักซ์อยู่ในพื้นที่ต่างๆของขดลวดนะครับแต่ว่าเราไม่จำเป็นต้องเคลื่อนที่ก็ได้นะครับใช้สวิตช์เอานะครับสวิตช์ก็คือจะบอกว่ามีสนามแม่เหล็กไม่มีมันก็เกิดการเปลี่ยนแปลงฟลักซ์ได้เหมือนกันอันนี้ก็ก่อให้เกิดการเกิดกระแสไฟฟ้าเหนี่ยวนำขึ้นได้นะครับส่วนนี้เราก็มาประยุกต์ใช้นะครับสูตรของฟาราเดย์นะครับก็ใช้สูตรของฟาราเดย์ไปนะครับก็มีหลายอย่างนะครับโอเคไหมก็ค่อยไล่นะครับ3ตัวแปร B A ไฟนะครับว่าอันไหนมันเปลี่ยนนะครับขึ้นกับโจทย์ผมตอบไม่ได้นะว่าใช้อันไหนจับไปแทนเลยไม่ได้มันต้องขึ้นอยู่กับโจทย์เราต้องพิจารณาว่าแมกเนติกฟิลด์สนามแม่เหล็กเปลี่ยนไหมพื้นที่หน้าตัดขดลวดเปลี่ยนไหมนะครับแล้วก็มุมนะครับเปลี่ยนไหมถ้ามุมเปลี่ยนส่วนใหญ่มันจะเป็นเจเนเรเตอร์นะครับเพราะขดลวดมันหมุนไปมาหมุนตีลังกามุมมันต้องเปลี่ยนแน่นอนครับแต่ว่าถ้าทุกอย่างเซตอัพนิ่งๆนะครับมุมจะไม่เปลี่ยนขดลวดถ้าไม่ดิ้นนะครับมุมจะไม่เปลี่ยนแล้วก็พื้นที่หน้าตัดจะไม่เปลี่ยนครับส่วนที่จะเปลี่ยนส่วนใหญ่ในโจทย์ครับก็คือสนามแม่เหล็ก B นะครับเห็นไหมเขาก็จะบอกว่าเดลต้า B ต่อเดลต้า T มาเท่าไหร่อะไรอย่างเงี้ยนะครับคุณก็ไปพิจารณาเองครับก็สำคัญนะครับถ้าเขาบอกไม่ที่จุดคุณต้อง take absolute value นะครับแล้วก็เวลาแปลงจาก EMF มาเป็นกระแสใช้กฎของโอห์ม VIR นะครับอยากทราบ I ให้เอามือปิด I คุณจะได้ V อยู่ข้างบน R อยู่ข้างล่างนั่นคือ I เท่ากับ V ส่วน R แต่ V มันไม่ได้ตรงๆแบบวิชาวงจรมันจะเป็น Epsilon นะครับ Epsilon ก็คือ EMF นั่นแหละ Electromagnetic Force นะครับก็วันนี้ก็คงจบเพียงเท่านี้นะครับแล้วก็คงจะต่อวันศุกร์หน้าจนจบบทนี้ขึ้น Generator นะครับเขาก็บอกตารางสอบไปภาคมาแล้วโอเค sorry for being too late you should have time for your for taking the rest right so if you have any question just let me know if มีคำถามอะไรนะครับก็โปรดบอกนะครับผมเก็บ2 คนอยู่ที่ YouTube นะครับคิดว่ากดอัดไปได้ด้วยดีนะครับมีตอนต้นมีอินเทอร์เน็ตหลุดนิดหน่อยถ้าไม่มีอะไรแล้วนะครับก็คงจบเลคเชอร์ไว้เพียงแค่นี้นะครับพบกันพรุ่งนี้เช้าสวัสดีครับบ๊ายบายครับโอ้ดีเลย